Hi, my name is Francine Marlot, and I'm a professor of astrophysics at the University of Innsbruck in Austria. My main research area is galaxy formation and evolution. I'm very excited to present to you today some of the first scientific results from observation of dwarf galaxies from the Euclid Space Telescope. So what are dwarf galaxies? Shown here is a beautiful color image of the Perseus galaxy cluster taken by Euclid. In this image, one can see many different types of galaxies, but in particular, the very bright, massive galaxies. Now, dwarf galaxies are much fainter and smaller, so they're more difficult to detect, and they're more difficult to see in this image. So here are a few examples to show you how they look as compared to the bright galaxies. Now, the fact that they're small and that they're faint doesn't mean they're not important. In fact, they're incredibly important for our understanding of the cosmos. They are some of the oldest and simplest types of galaxies, which helps us understand how galaxies form in the early universe. Also, based on our current understanding of structure formation, the massive galaxies that we see today, like our own Milky Way galaxy, formed over millions of years from the amalgamation of all these smaller structures, galaxies. And finally, they have a large dark matter content compared to their stellar mass as compared to other types of galaxies. So they are an ideal laboratory for studying dark matter. So what are the latest results from the Euclid observation of dwarf galaxies? In this image is shown in the gray larger square, the area covered by the Euclid observations. And in the smaller square, the area or regions covered by previous Hubble Space Telescope observations. So one first very important capability of Euclid is its very large field of view. And here it's well illustrated that we can cover a much larger field of view in a single observation than other surveys. And one of the main results of our work has been detecting over 1,000 dwarf galaxies in this region. They are highlighted here by the green symbols. Every symbol is at the location of a detected dwarf galaxy with Euclid. And of those, over 600, so more than half, are completely new discoveries by Euclid. When we zoom in on the image, we see the other amazing capability of Euclid in terms of its high spatial resolution and its crisp image, so its sharp image. With this, we're able to quantify the properties of the dwarf galaxies, some of which are shown here. We can look at their morphology, we can look at their structure, their brightness, and their size. But not only that, again, because of the high spatial resolution, we can detect and identify central nuclei, for example, or globular clusters that are orbiting these dwarf galaxies. And so this is part of the results that we have presented in our work. They are expressed here in terms of these pie charts, in terms of the center of the charts, the morphology, and in the outskirts, how many nuclei are found, how many globular clusters are found, and how many show morphologies that are disturbed due to tidal interaction or mergers. The bottom plot shows a comparison with previous samples in terms of the magnitude and size of our dwarf galaxies. And we find that there are very good agreement between the properties that we measure and previously known properties of dwarfs. In addition, we also find more diffuse dwarfs than in previous works. And for the future, we are looking forward to doing the same kind of research in the Euclid Wide Field Survey, which will cover a much larger area on the sky, and therefore will allow us to probe and to search and to characterize a much larger population of dwarfs with different characteristics, with different masses, located in different environments and at different distances, helping us build a much more detailed picture of galaxy formation and evolution.